Good afternoon, and thank you all for attending our presentation today on a concept design of a combatant craft mothership, the USS Chicago AFS-MRs-1. So first, we're going to start out by introducing the team. So starting with Annabelle Bornbush, she's from Island Heights, New Jersey, and she has work experience at CCD Carderock, MSC, USMI, and has dinghy and offshore sailing experience. Next, hello, I'm Everett Bowanek. I'm from Toms River, New Jersey, and I worked at Metal Shark Boats, Croatia, Stolt Tankers, and General Dynamics Electric Boat. Next, we have Ethan Desjardins. He's from Boulder, Colorado, and he's worked at Resolve Marine Group, Delaware River Bay Authority, and General Dynamics NASCO. Finally, we have Brian Keeley. He's from Cranford, New Jersey, and he's worked at Draper Lab, Brookhaven National Lab, and MSC. So for a brief overview, we'll be talking about the vessel's mission, the vessel particulars, propulsion and machinery, mission systems, major systems, weight centers and stability, and then we'll have a conclusion. So to start off, our mission is to create a float-forward staging vessel. The vessel should provide a platform for the operation and maintenance of 16 11-meter by 3-meter combatant craft, UAVs, one Sikorsky Black Hawk helicopter, 94 MSC and U.S. Navy crew. It should also permit operations in littoral waters, maintain self-defense capabilities, and reduce fossil fuel reliance by 25% compared to similar vessels, and operate for 24 hours without fossil fuel emissions. So above, you can see our vessel principal characteristics. We were limited to a maximum draft of 5 meters. Our weights and centers showed that our initial draft estimates were likely high, so this did not become a strong consideration for us. Our original length to beam ratio, based on preliminary power requirements, was deemed to be low and the power was too high, so the vessel was extended to 135 meters. For our general arrangement, our main features consist of a large well deck for storage of 12 boats. In conjunction with that, we have the stern ramp launch and recovery. For housing of the 4 remaining boats, we have 4 boats launched from the weather deck davits forward and aft, and the aft helipad, which can both house the helicopter and launch UAVs. Finally, with all the weapon systems, we have a total 360 degrees of weapons coverage. For our hull form, the hull form was developed in Rhino 7 utilizing the hull assistant feature. Parameters such as max area location, prismatic control, flare, fullness, and bow rounding were selected to try to get the hull shape to match the Freedom-class littoral combat ship and Arleigh Burke-class destroyer to meet the 25-knot speed requirement, while still allowing for a large beam for the aft end of the well deck. This model allowed for the development of a lines plan, which you can see up there. And with this, we were able to utilize GHS for stability calculations and NavCAD for powering requirements. We used a combination of the Holtrop and Fung predictions in order to get preliminary powering requirements. For our propulsion system, we opted for a twin-screw diesel-electric powering arrangement to allow for higher maneuverability with split thrust and to reduce the propeller size. The diesel-electric engines allowed us to move the engines forward towards midship to accommodate for the well deck on the aft end. We selected 4 Wärtsilä dual-fueled engines, mainly to have extra redundancy and for the capability to burn methanol to meet our emission requirements. We have a total installed power of 19,820 kilowatts. For our propellers, the propeller speed was limited to 250 RPM for vibration concerns. In order to have adequate clearance between the bottom of the hull, the shaft was angled down by 1 degree and set to 3.5 meters in diameter, which gave a clearance of 1 meter or around 30% of the diameter. Professor Hadler's propeller regression equation was utilized, giving a propeller pitch of 3.15 meters. From this, the pitch to diameter ratio was established at 0.9, and the propeller efficiency was determined to be 64.4%. Next, to begin the rudder selection process, Wärtsilä's rudder sizing equation was utilized to find a general rudder area. This gave us a blade area per rudder of 9.2 meters. We then assumed that it was a NACA 00 type rudder with a constant cross-section across the span, which allowed for complete sizing of the rudder and needed steering gear. Next, I will invite Annabelle up to talk about the machinery arrangement.
Thank you, Everett. Our machinery arrangement was primarily affected by our major vessel system of combatant craft launch and recovery, which we placed an aft well deck on the vessel. This forced us to move our machinery spaces forward within the vessel. To accommodate this, we selected a diesel-electric arrangement with 2 primary and 2 smaller secondary generator sets, as Everett discussed prior. This helped with size constraints and allows for flexibility with powering efficiency at low load configurations. It is important to note that all auxiliary machinery was primarily sized based on our parametric analysis and similar ships. As you can see on the screen is a plan view of our machinery spaces. We have our tanks here, the aft of the tank top level, and then in the forward on our tank top level, we have our pump room and our marine sanitation device. On second deck, we have our electrical equipment, our HVAC room, our compressor room, and our freshwater generation room. First, I'll start auxiliary systems by discussing fuel oil, lube oil, and hydraulic oil. We size our diesel fuel capacity based on a need to run all 4 generator sets at a maximum continuous rating for our full range of 6,000 nautical miles. We arrange these tanks to minimize free surface effects as well. Our service tanks were sized to have a capacity to run, again, all 4 gen sets at MCR for 3 hours in accordance with Bureau Veritas rules. To accommodate that 24-hour no fossil fuel requirement, we used methanol. This tank was sized to run, again, the 4 engines at MCR for that 24 hours. And we have hydraulic oil and lube oil capacities, which were sized based off of similar vessels. Here's our fuel system arrangement, which was primarily split up into port and starboard sides, which were then interconnected to provide redundancy to the system. The system was arranged to reduce the net positive suction head required to prevent cavitation within all of our fuel pumps. And the fuel system includes supplies to the combatant craft refueling system, to the emergency generator, and also to the aviation fuel tank and supplies for our helicopters. Here's our fuel piping schematic. It's important to note that all components in all of our systems were designed with compliance to Bureau Veritas rules. For potable water and fresh water, we have a potable water capacity for 5 days for our full 94-person crew at 200 liters per person per day. We also have some freshwater capacity on board for other systems, such as the combatant craft systems. To provide these capacities, we have an RO plant and a freshwater evaporator on board the vessel. For gray, black, oily, and bilge water, we have an aggregate capacity of gray water of 21 cubic meters. We have some black water capacity, and we also have a marine sanitation device installed on board. It is based off of similar vessels, and we selected a Red Fox 2000, which is sized for 100 persons. We have an oily water capacity on board, and we have an Alpha Laval centrifugal separator. We also have split up our bilge systems into oily for the engine spaces and a clean bilge space as well. For our HVAC system, we have 4 air coolers, which were selected to provide adequate cooling of the vessel in a wide range of operating environments. We have 2 air heaters, which were selected to utilize waste engine heat to heat the vessel in cold environments. We also have 2 refrigeration units, which would provide cooling to the fridge and freezer spaces for provisions and stores. We also have a fan space allotment all throughout the vessel in the superstructure and in the hull to account for ventilation of the engine room and our accommodation spaces. We also have life-saving equipment on board, which is sized in accordance of 46 CFR. We have 2 freefall lifeboats on either side of the vessel, the capacity of 34 persons for our full civilian crew. We have 8 sets of 12-person life rafts per side to provide for our full 94-person complement. We also have firefighting equipment on main deck, and we also have space allotment throughout the vessel for these systems. I'll now pass the presentation off to Ethan to speak about mission systems.
Thank you, Annabelle. So to kick off our mission systems, first we have the ship's offices. On the O4 deck, we have meeting and office spaces for the deck and engine departments. And there is also a large space on the main deck dedicated for the combatant craft department. All accommodations on board follow the NAVC guidelines for shipboard habitability, which includes laundry and head requirements. Common spaces were provided on every accommodation deck. There are 2 gyms, one dedicated to enlisted personnel and one to officers. The main galleys are located on the O2 deck with space for an officer's wardroom. And a separate civilian operated galley would serve all MSC personnel on board. For communications, or for the Combat Information Center, we have one located on the O2 deck, which provides the vessel commander and crew with critical tactical information for command and control of the vessel and its fleet of small craft. For communications, we have a navigation bridge located on the uppermost deck of the superstructure. This allows for a wide field of vision and clear sight lines over the bow. Just after the navigation bridge is a secure radio room for communication and online security. Adjacent to this is a conference room, which could serve as a meeting space or be used for large-scale conferencing with short-side installations. And space was also allotted for technical and logistics support, which includes VHF radio, GPS, depth sounding, satellite data, and more. So for the combat craft operations, we have the launch and recovery staging area on the aft end of the vessel. And we also have 4 main deck davit launch craft. To meet the service and maintenance requirements, there's space for simultaneous work on 3 craft at any given time. And here in the plan view, you can get a better view of the well deck, the repair garages, and the storage areas for parts, as well as the combat craft refueling system, which consists of the service tank, refueling manifold, and dispensers located throughout the vessel. And it should also be noted that the fuel for the combat craft is the same marine diesel oil that the combatant craft mothership uses for ease of refueling. Here you can see the access hatch on the main deck, which allows for vessels to be raised and lowered into the well deck. And this is accomplished by the A-frames that are sized accordingly. For the launch and recovery system, we have 25% of our combat craft capacity located on the main deck for deployment in less than an hour and sea state up to 4. 75% of our combat craft is stored in the well deck, resting on an angled ramp with rollers. When launching, the stern ramp would be lowered into the water and craft can slide off. Pictured above is an example of one such system from Solis Marine. And this specific system can be sized for a variety of uses and vessels. The well deck craft are arranged in 3 rows of 4, which allows for ease and speed of launching. And there's also an overhead gantry crane located in the well deck so that the craft can be moved during storage. For helicopter operations, we have the aft helipad and an attached monitoring system. The fuel dispenser and service tank for the aviation fuel is located in the superstructure adjacent to the repair garage. And the flight operations bridge is located on the aft end of the O4 deck, allowing for the operators to overlook the helipad. To maintain our self-defense capability, we have 360 degrees of weapons coverage, which is provided through 1 Raytheon rolling airframe missile system, 1 Raytheon Phalanx close-in weapon system, 2 Mark 38 25mm deck guns covering the flanks, and 4 50 caliber guns placed to cover the bow and stern areas of the ship. There's also a small arms locker on the forward end of the superstructure on main deck, and a magazine for the storage of the ammunition of the previously mentioned weapon systems. Moving on to our structure, we selected HSLA 80 steel, and the vessel was longitudinally framed, which is common for similar sized surface combatants. We fully comply with Bureau Veritas rules for the minimum section modulus and moment of inertia at midships, as well as the requirements for plating thicknesses and member thicknesses. Using our new structural arrangement at midships, we scaled the weight throughout the vessel using sectional areas to attain an updated weights and centers that ended up being within 8% of our original SWIBIS estimate. I will now invite Brian up to talk about the electrical system, stability, and weights and centers.
Okay, thank you, Ethan. So now I'll discuss the design of the electrical plant. The main distribution scheme you can see is on the figure on the right. Starting from the top down with the main switchboards, those are generated at 6.6 kilovolts from 2 main diesel generators and 2 smaller diesel generators, all of which are of Wärtsilä make and model. The largest load on that bus is by far the 2 prop motors, which require at a speed of 25 knots, 7,835 kilowatts. Moving down to the 480 bus, this switchboard supplies the majority of the main machinery, most of which is located on the 3rd deck at tank top level and in the pump room. Transforming to 120 volts on the low voltage side, this switchboard supplies all hotel loads and lighting in the superstructure. We have an emergency switchboard fed by an EDG, 2 switchboards. First is the medium voltage at 480, and that, as per DDS 310-1 NAVC requirements, supplies emergency steering and launch and recovery systems. Those are 2 emergency requirements for amphibious type craft, which this vessel is most similar to. Transform to 120 volts is an emergency switchboard for lighting and communication systems as per NAVC regulations. Some electrical equipment includes 4 transformers shown on the slide. It's important to note that 2 of these are for emergency purposes. The first is on the EDG distribution scheme on the left. However, transforming from the high voltage bus to the 480 volt bus, there's also an emergency transformer that can be switched on and off in the event of damage to some of the generators. Of course, the 4 main generators previously discussed, the 1 EDG, and then various smaller items such as insulation protection, ground fault monitoring, and electrical interlocks. Moving on to the weight centers and stability, a few metrics are shown on the slide. In a lightship condition, we have a displacement of 3,310 tons and a draft of 4.42 meters, which complies with our 5-meter draft requirement. This displacement estimate was taken from our initial SWIBIS estimate and then also from our updated weights and centers, which, as Ethan mentioned, strongly agreed. Our GMT in this condition is 1.86 meters, which was surprisingly high. However, owing to the large size of our generators, this made sense. Comparing the full load departure and full load arrival conditions, our displacement decreases marginally by about 100 tons. And interestingly, our GMT increases. This is because in the full load arrival condition, we were permitted to have ballast as per the deliverable requirements. So we had a slight increase in GMT, even though that fuel oil stores were reduced to 10% and the black and gray water tanks were increased to 98%. A few other metrics you can see are the draft requirements. In the full load departure condition, our draft was 4.76 meters compared to 4.56 meters in the arrival condition. Moving on to our intact stability. Those metrics are shown on the slide for all 3 conditions. Primarily, we used IMO intact stability code from 2008. This code complies also with BV intact stability codes. In the full load departure and full load arrival conditions, we met all stability requirements in regards to GZ riding arm curves and integral curves. The lightship condition does not meet the stability requirement owing to 2 items. First, the integral GZ curve between 30 and 40 degrees is less than the IMO threshold. Secondly, it's also below the threshold for the absolute angle at maximum GZ. Functionally, the peak of the GZ curve occurs too soon to comply with code. As can be shown in the table, our absolute angle at our maximum GZ was near 53 degrees for the full load conditions, which complies with IMO. However, compare that to the lightship condition without any liquids or ballast, that decreases dramatically. Moving on to the damage stability, we applied a 76 millimeter margin to our floodable length curves as per the requirements in 46 CFR. We have 7 continuous watertight bulkheads subdividing the hull, and the output from GHS are shown on the slide with our floodable length curves. And our full load departure, arrival, and lightship conditions all pass the 1 compartment flooding criteria. 2 compartment flooding criteria failed in all 3 loading conditions owing to the large extent of the well deck. It was unavoidable in the design of this ship that we would have to have a large open space to accommodate the fleet of combat craft. Further iterations of the design might work on distributing the boats better so that we can have increased subdivision and meet those requirements. And in a worst case damage condition, it's expected that the flooding of the well deck would cause significant issues. This was confirmed using the GHS load editor and those outputs. Primarily, this would decrease buoyancy, introduce a large free surface moment if underway, and also lower ship stability and increase the trim by the stern. Finally, I would like to thank our industry mentors, starting with Jeff Bolz from Gibbs & Cox, Vicky DeLuca-Kecke is a private consultant, Catherine Geisler, Scott Henry, and Dean Schleicher from NAVSEA, Luke Sullivan from Serco, Matt Unger from Unger Marine, and Jeff Putmark from Transtech and Ship Shares LLC. We thank everyone for being here today and for consulting on this project. On the website of things, I'd like to thank Professor Golden, Professor Boyd, Professor Martin, Dean Werner, and Professor Harris for their help and guidance. Now, with that being said, I'd like to open the floor to questions, and thank you for listening.
I'd like to ask what considerations go through in determining what propulsion and electrical plant to go with. He's done integrated electric drive. About that.
Sure. I think I can take that. I worked on the electrical system. So primarily because we decided for a well deck, that automatically eliminated some of the direct drive options because we had to actually angle the prop shaft below that well deck area. That was our primary space constraint. In vessels of similar dimensions, such as an Arleigh Burke destroyer, some of the LCS ships, those all use LM2500 gas turbines as is standard for naval regulations. So a diesel electric was chosen because we needed to segregate the engine room and also push it closer to midship. That was considered better for stability owing to the really large size of the Wärtsiläs we chose. In regards to the electrical plant, I think in a second iteration of the design spiral, we would opt for a ring bus. Modern naval ships tend to all use ring bus systems, although in all honesty, I was not aware of that at the time of this design. So that being the case, it should be a ring bus system. We opted to segregate into first three main switchboards. Typically, I think there's actually two low voltage switchboards on USNS ships of a similar mission. I'm not exactly clear in regards to those regulations. We primarily use NAVSEA DDS 310-1 for all the electrical things like load factors and design criteria. So yeah, does that answer your question? Okay, thank you.
Thank you. I wanted to ask about the tankeration. So on the arrangement that you showed us, it looked like the fuel oil tanks were right up against the side shell. Is that correct? And if not, what was the choice on the distance from the side shell?
Give me just.
Thank you for bringing it up.
Yeah.
Yes, so it looks like it's right on the hull.
Yeah, so the question was, what considerations were given for the fuel oil tanks and if they are directly on the side shell? So not depicted in the machinery arrangement here, but there is a wing tank that's about 1.5 meters throughout the side shell of the vessel. And we also included cofferdams that you can kind of see in between each of the separate tanks to just separate them. So they are not directly on the side shell. There is a wing tank, and there's also the ballast tanks located underneath to keep them off the bottom shell.
Thank you.
Yep.
Okay, questions that come from online. Can you please comment on the use of the transverse stairs as opposed to longitudinal stairs?
Yeah, sure. So commenting on the placement of stairs, it was determined during the initial design of the vessel when we were modeling things in Rhino 3D and doing the analyses in Orca that to fully, at least in regards to the stairs in the deck, or rather below deck in the hull, we didn't have space longitudinally to fit the stairs we wanted to. So there had to be some interesting arrangements in that regard. Transverse stairs were decided mainly for that reason. I won't go into the niche technical details of it, but there wasn't sufficient longitudinal space. And this was also the case in the deck house, I'll add, owing to the relatively high crew requirement of 94. So transverse stairs were considered the most feasible option, though we do understand that there are safety regulations around that in regards to heavy seas and rolling. So
just adding on to that. So we wanted to maintain the structural continuity running vertically. So for the bulkheads and the staircases, just owing to the fact that the well deck took up a very significant portion of our structure. We didn't have the longitudinal length, as Brian mentioned, to be able to maintain that continuity with longitudinal stairs.
Okay, great. Another question, can you please comment on the selection of fuel grades that you're using?
Yeah, so I'll comment on that. Fuel grades, primarily we were under the assumption that we were using F-76 military diesel. We didn't put a significant amount of research into this. However, it was our understanding that USNS type ships all use F-76 diesel. So based on that being a standard in at least some parts of the US Navy, we determined that in this case for preliminary design would be a reasonable choice. Personally, I'm unsure as to the variation in diesel grades for the US Navy, though I believe F-76 is the standard. So I hope that the question.
Okay, next question. Comment, couple of questions, comments. Stern ramp. The comment is the drawback of is a foul stern ramp reduces the ability to get vessels off of the ship for repair. Can you comment on that?
Yeah, so just commenting to if for some reason the stern ramp was inoperable, the access hatch from the main deck down into the well deck is capable of raising and lowering vessels in and out. And then the A-frames could be used to launch them over the side of the vessel. So in the case that the stern ramp was inoperable, there is still a means to move and deploy the combat craft, but it would definitely take a very long time.
Another question you have here. Helicopter rotor, is it clear of the aft bulkhead of the superstructure?
Yes. So just the clearance, the question was about the clearance of the helicopter blades themselves. So there is about, you can't really see it there, but there's about 20 meters of space between the aft end of the superstructure and where the helicopter blades would be there on the helipad. So I'm not familiar with specific rules on helicopter operation, but it does have about the diameter of the blades themselves of space from the aft end of the superstructure.
Okay. Next question. This person says they don't see much ballast capacity aft. Will you have excessive trim forward after the discharge of the small craft in the well deck?
I think I can answer that. So the question was that they do not see much ballast capacity aft, and what we see, I guess, yeah, trim by the bow once the combat craft is discharged. The answer is no, I don't think so, because during our loading condition test, we are trimmed by the stern almost 1 degree, and removing that load of the combatant craft from deployment, the trim is still reasonable and still trimmed by the stern a little bit. So the answer is no, it will not affect it too much.
Okay, great.
I'll also just add one more thing. Because our engines are so large, owing to a 25 knot speed requirement, a lot of our longitudinal stability is derived from that and having a large mass fairly close to midships. So that's why we don't see as much trim as you might expect.
In the midship section, please get some sort of discussion. What exactly are we looking at? Are there some kinds of frame vertically oriented down the top side?
You want to take the outboard picture?
Can we repeat the question, please?
Yeah. I think this question of is there some kind of frame vertically oriented down the top side?
In this image, no, but in reality, yes, there would be. Yeah.
Okay, maybe part of that question is that a wing tank? What is that in there on the side shell?
Inside the side shell, those are wing tanks. Yes. Yeah.
So those are the wing tanks there, as the question before asked, and there would be web frames located throughout those. So that I'm not sure if that answers the question specifically, but
There's a follow-on question, the same person. So, the arrangement was also flagged as very tall and narrow beam. How does the team plan to address this going forward? An early slide mentioned VCG. Can we get further discussion on this?
Yeah, so I'll address that regarding the height of the vessel and its relative slenderness. In future iterations, those comments are acknowledged, and we also recognize the issues with that. The reason for the slenderness is really due to the speed requirement. Our fruit number was sitting at about that of something like an Arleigh Burke or a little higher because we needed to hit 25 knots. Now, similar ships with a comparable speed requirement all are powered by gas turbine, at least in the US Navy. So in future iterations in the design spiral, it's likely that the ship would have to be scaled up effectively in all dimensions. The reason for that is to improve stability transversely, we would increase the beam. However, owing to our 5-meter draft limitation, functionally everything has to be scaled to that level. So yes, in the future, that's something we would do. Because this is a small ship design class, going back to the practicalities of it, we've tried to keep it within, sub 150 meters, just so things didn't get enormously large. However, to do it functionally, yes, it would have to increase in size, and that would likely resolve those issues.
Okay. There were circular tanks included on the GA. For what reason?
I can take that. So yeah, we had certain tanks made circularly. I think it was the fresh and potable water tanks. That was just selected because of ease of construction. We figured that installing a circular tank in the section, because they're not joined to a bulkhead or to one of the other structural elements. So just for ease of construction, it was a mentor that advised us to make the tank circular.
The last one is more of a comment, it looks like, than a question. The helicopter blades do not appear to be clear when spinning, and blades are oriented longitudinally.
Yeah, so
Can you just comment on the halo array?
Yeah. If you put that up first.
This one shows a quick wall.
Yeah, okay. Yeah, so in this depiction in the helipad, we are aware of the issues regarding helicopter clearance, particularly tip clearance between the helipad and the nearest point of crew operations. This particular version is scaled from a Sikorsky Blackhawk helicopter, and in all honesty, for something like this to work in regards to regulations on a ship still of this size, I'm not certain that type of helicopter could be accommodated. So yes, we would have to increase the overall size of the helipad, which accompanies the overall increase in length and beam, as I mentioned before in the previous question. So a lot of those issues are still resolved by overall scaling the ship up.
Okay, well, that's great. Are there any other questions? Okay, thank you very much.
Thank you.